Oh, the infinite
sequence.
What are you doing your 3D also, come on.
What are you talking about? Okay, now this is actually very important, right? Because we've been talking about and looking at videos and stuff a lot lately, and there's like this cool effect. It's called the Droste effect. Basically, you have a picture of yourself, and then you can get pictures within that picture, which has that picture, and it's kind of like Inception. Like you keep going down through all the layers, right?
Have you ever done the mirror thing?
How do you do it with a mirror?
You're looking into a mirror and you get like
another mirror. Yeah.
Do like that and
yeah.
It reflects.
Like keeps bouncing back and forth, kind of. Yeah. So the same idea. This is just with like a webcam that I had and my phone, like a selfie camera, and like the thing just keeps going in and in and in. And there's like a lot of examples of stuff you can find like this. And the idea is that this is very close to what recursion is. So a recursive formula is when we define a term that's happening and all the other terms following that using the term itself. So let me give you an example. Let's give you these numbers here. Right? Let's take these numbers. 0, 1, 3, 7. 15, 31, 63. Cool. So these ones here, see if there's a pattern where you can use a previous term and use it to define the next term, if that makes sense. So like, what do I need to do to this to get to the next one? What do I need to do to this to get to the next one is what I'm thinking. If you can work that out while I write this question.
Do you want to tell you what it is?
Yeah, what is it? Sorry.
The adding 2 to the power of something each time.
So what, 2 to the power 0? 2 to the power 1? No. 2 to the power 1. 2 to the power 2. 2 cubed. 2 to the power 4. Is that what you're saying? You're adding 2 to the power something each time. Yep. But I want to define it in terms of, because this idea of a recursive formula, right? I want to define this. I want to do something with this and get to that, if that makes sense. Yeah? Does that kind of make sense what I mean?
Yeah.
So like I want to do something with this and then something else and get to this. Do something with this and something else and to get to this. I wonder if you can try to work it out.
Yes.
What do you got?
You get that number.
Yeah.
And then you add it on, but 2 of it.
Yeah, so you do times this by 2, add 1. Times this by 2, add 1. Times this by 2, add 1, so on and so forth. So this is how we can define a recursive formula, right? I'm saying I do something with this, I get to the next one. Do something with it again, I get to the next one. Very common thing in terms of programming because you can like use functions that are recursive. You can like complete an action and then keep doing that action multiple times until you need it to do whatever you need to do, right? So the way we define that using mathematical notation is that, okay, they'll define a sequence, something like this as, okay, I'll give you the first thing, which is this guy, yeah? And then to get to the next one, so A sub n, that's equal to, what do you say, 2 times the previous one, right? So that's 2 times, what would the previous one be if the current one is n, if I want to go back? N minus 1, right? And then you add 1 onto it. Yeah. So the sequence is defined as this. They'll give you like an initial term and they'll give you like a general expression, yeah? And this idea of a recursive formula, so in order to prove it, they'll ask you to do this. They'll say, can you prove by induction that another way we can write this, now you talked about 2 to the n, another way to write it is 2 to the n minus 1. So if you think about, okay, what's 2 to the 1 minus 1? That's just 1. 2 squared minus 1, that's just 3. 2 cubed minus 1, that's just 7. So these are 2 ways of defining the same thing. But the idea with induction and recursive formulas is that they'll give you the sequence, okay? You can use this, but you need to prove this is true, okay? So that's the idea with these first order recursive formulas in extension 2 with induction. How do we prove this is true? Same steps, right? I'm even sick of seeing this, but it's a great structure that works, right? So it's test true for, now here notice, right, like we're looking at now n greater than or equal to 0, and we're substituting this stuff into, right? This is the one that we're trying to prove. This one will come into play later in step 3, but for this one, we're just going to start with this guy, right? So a sub 0 is equal to 2 to the 0 minus 1, and that's just 1 minus 1 and that's just 0. And how do you know this is true, right? Well, because it satisfies your definition. Like they're giving you this is something that's defined and we can use it. Yeah. Does that kind of make sense?
It's supposed to be equals to 0 or just like n greater than equal to 0, is that?
Yeah. So we start n, this guy, as the like 0th term, if you want to think about it like that. Yeah.
So why put the y greater than that?
Oh, sorry. Yeah, you're right.
It is just equal, okay.
Yeah, equals 0. Yeah, cool. So it should be, and this is the same as the definition. So that's how we know it's true, right? So therefore, is true as it is the same as the recurrence definition. It's going to be a similar idea, but now we just got like different things going on here. So assume true for n equals to k. So I'm looking at this thing. This is the thing that I'm trying to prove. And I'm assuming that's going to be true. A sub k is equal to 2 to the k minus 1 for k greater than or equal to 0. And then step 3, prove true for n equals to k plus 1. Now generally these aren't actually harder, but it's just getting comfortable with using the notation and definitions and things like that, right? So prove true for n equals to k plus 1, I need to prove this. A sub k plus 1 is equal to the 2 to the k plus 1 minus 1. That's what I need to prove. How do I actually like start this off? Now this is different to like using your inequality ones or your divisibility ones, because again, there's no actual numbers to work with and there's no real operations you can use to prove this. What do we have though? What are we given? We're given this definition, right? This definition is something that we can use, right? So, and remember, this is just like an example of this. Like you're taking 2 times the previous one and you add 1 to it. That's this idea of a recursive formula, right? So what I'm going to do is I'm going to say from the recursive definition, I can take, all right, what would a sub k plus 1 be? That would be equal to 2 lots of a, now what's k plus 1 minus 1, right? Well, then that's just k, yeah? Plus 1 here, yeah? And so the idea is I have this, I can use this, but what am I trying to get to? I'm trying to get to this. That's what I'm required to prove, right? What do you reckon I can do with this? Any pieces here?
Yes.
Yeah? Yeah, up here, right? So a sub k. So that's equal to,
Oh, no, see.
you can see it?
2. This is even easier.
It's even easier. I tell you, it's not meant to be hard, right? It's just getting comfortable with the definition. Because when you substitute that in,
Oh, it is a bit.
right, when you substitute it in, then you get something like this. And I'm trying to get to this guy. Well, if I expand this out, so 2 times 2 to the k minus 2 plus 1, then I'm just going to get 2 to the k plus 1 using my index laws. And then that's minus 1 when I put it in. Right, so from the recursive definition, I do end up with this, which was, I guess that actually was LHS, I should have said that, which is equal to RHS. And using this recursive definition, now not with any kind of like algebraic like values that we're trying to substitute and things like that, we substitute this guy in here, but we have to use this definition here, right? Therefore, it is true for n equals to k plus 1, and for all n greater than or equal to 0 by mathematical induction, PMI. So this is the idea of recursion, right? It's a different way of thinking about things. We're defining this sequence in terms of the previous terms in the sequence, and we're using induction to prove that another way to write it is using this method. And like you said, right, the algebra is actually not very difficult. I think that's the intention. It's just being comfortable with the notation and things like that, and they can make some tricky ones. I'll show you that later on another time.